In this video, we will be talking about some physical applications of line integrals. Now, we will not be covering all the applications that exist in all of the world. You're going to encounter quite a few more line integrals, for example, depending on what kind of engineering and physics course you take. I believe that line integrals have many additional applications in electrical engineering and electromagnetism, for example. But for today, we are just going to be focusing on these two applications. We're going to be talking about how to use line integrals of scalar fields to calculate the mass of an object that is functionally acting like a wire, shaped like a wire. We'll also be using line integrals of vector fields to calculate work done by a force that might be variable acting on an object that might be moving along a curved path. So beginning with our first example, mass of a wire-shaped object, let's go back in time to our previous mass calculations. For example, if we had an object in two-dimensional space, occupying a two-dimensional region called R, and if that object had a density which could be different at any particular point, then we could find the mass of this two-dimensional object in the following way. We could use a double integral over the region R occupied by this object of that two-dimensional density function. And that double integral would find the mass of this two-dimensional object in two-dimensional space. It was similar for a three-dimensional object with a three-dimensional density function. If you had a three-dimensional butternut squash looking object, for example, occupying a three-dimensional region called E, then you could find its density using a triple integral over that region E of your three-dimensional density function. But suppose instead that you're working with an object that is for all intents and purposes one-dimensional. For example, a wire or a thin cord. But perhaps the wire/cord is slightly bent or twisted or curved, so that even though it is one-dimensional, functionally speaking, it cannot be treated as living in one-dimensional space. The one-dimensional wire lives within two-dimensional space, or the one-dimensional wire lives within three-dimensional space. In this particular case, if you want to calculate the mass of an object in these situations, the technique that you need to use is a line integral. So the formula that we have is as follows. If your object occupies a curve called C in either two-dimensional space or three-dimensional space, and if you know the density of that object at any particular location, then you can calculate the mass of the object by taking a line integral of the density function over the curve called C. This works in both 2 dimensions and in 3 dimensions. For example, suppose that we have an object which is occupying a circle. So we have a wire, we have a coil, we have something whose shape is a circle of, in this particular problem, a circle of radius 3. Now, what is the density of this coil at any particular location? The density of the coil is given by the function rho of xy equals x squared plus 1. Excuse me, y squared plus 1. So to sketch this situation, our object resembles a circle of radius 3. And for example, the density at this location here, where x is equal to 1 and y is equal to 0, the density at this particular location is equal to 1 unit. But if I went up here to the top of the circle, where the x and y are equal to x equals 0 and y equals 3 respectively at the top of this circle of radius 3. In this case, the density would be given by y equals 3 squared plus 1, which would be 10 units. So it is significantly heavier at its top end and its bottom end than it is toward the middle. From this data, let's go ahead and calculate the total mass of this object. To that end, I'm going to have to calculate a line integral of this scalar valued function y squared plus 1 over this curve C that our wire occupies. So, as usual, the first thing that I'm going to have to do is parameterize the curve C. For a scalar integral, for a line integral of a scalar field, the orientation of the curve is not important, and it will not affect the final answer. So I'm just going to choose the simplest possible parameterization, the most common parameterization for a circle of radius 3, which is the counterclockwise one. X is cosine, y is sine, each multiplied by the radius. Now if I calculate r prime of t, then I get negative 3 sine and positive 3 cosine, and the magnitude of that vector, if I use the Pythagorean identity, the magnitude of this vector is just going to be the square root of 9, which is the number 3. And if I plug the parameterization into our density function, and I replace what was y squared with what is now 3 sine squared, I can express the density function in terms of this variable t as well. So let's put it all together. Let's transform this line integral into a single integral with respect to the variable t. The quantity that we're integrating has transformed into 9 sine squared plus 1. The length, the r prime magnitude, has become the number 3. Now, what will our t limits be for this circle? We will trace out the entire circle exactly one time as t goes from 0 on the bottom to 2 pi on the top. Now, to evaluate this integral, I'm going to have to rewrite sine squared using the power reduction identity to transform this into 1 minus cosine of 2t cut in half. Let's go ahead and find the antiderivative of that quantity. That 27 over 2 would become 27t over 2. The integral of this negative cosine will become a negative sine divided by 2 via u substitution because of chain rule. And then the integral of that 3 in the back will become 3t. Now it looks like this sine vanishes at both 2 pi and 0. So what's left behind? We're left behind 27 times 2 pi plus 3 times 2 pi, and all of the terms vanish at the lower limit. So after a bit of cleaning, this looks like 33 pi units for the mass of this object. So that's how we can find the mass of a one-dimensional object that is twisted or bent so that it lives in 2 or 3-dimensional space. Just do a line integral of the density. For our second quintessential example of a physical application of a line integral, let's consider work done by a variable force. To set the stage, let's go back to Calculus 3 for a second, and let's remember the formula for the work done by a constant force as it acts along an object moving through a straight line displacement. So an object is moving along a straight line represented by a vector d for this displacement, and as it is moving, it is being constantly acted on by exactly the same force, a force with exactly the same direction and strength throughout the entire journey. In this situation, the work done by the force on the object could be found by just taking the dot product of the force vector and the displacement vector. And work is super useful in a lot of physics and engineering applications because of something called the work energy theorem, which gives you a relationship between the work done by the force and the change in the object's kinetic energy. Now, suppose that the object is not moving in a straight line. Suppose that the path of the object is curved. Or suppose that the force that is acting on the object at any different location can be different in direction and magnitude depending on, where this object is in its journey. If you're in a situation like that, where the force can vary, and or a situation where the object is not moving in a straight line, in that situation, to calculate the work done, you would also use a line integral. In this particular situation, if I represent the path traversed by the object by a parameterized curve r of t, and if I represented the variable force by f of x comma y, then I would find this work done by doing a line integral of the force over the parameterized curve, over this parameterized representation of the object's movement. This formula is given in 2 dimensions, but it works just as well if your curve is 3 dimensional and your force vector is dependent on your 3D location. No problem. Alrighty, now for a concrete example, let us suppose that we have an object that does one clockwise loop around a circle of radius 4. And as it moves clockwise through this circle of radius 4, it is acted upon by a force. The strength of the force and the direction of the force is different depending on your location, however. And so the varying force is represented by this vector field. The force at the location x, y is given by negative y, comma x. So for example, if the object is located at this position, where x and y are equal to 4 and 0 respectively, then what force is acting upon the object as it passes through that location? The force would be given by negative y, so negative y would be 0 in this case, and then the y component would be equal to the x value. So the force at 4, 0 would be equal to 0, comma 4. And so that would be this vector acting straight up. Okay, so let's see the work done by this variable force on this object as it traverses this path clockwise. To that end, let's go ahead and set up a line integral. Now for a line integral, we're going to need to parameterize this circle, but this time, because it's a line integral of a vector field, we have to be careful to respect the orientation of this curve. Now I could try the quintessential parameterization of a circle of radius 4 for cosine and for sine. But this is going to be traversed in the counterclockwise direction. This is not going to have the correct orientation. Instead, to flip the orientation, I'm going to go ahead and make that input negative so that it gets swept out backward in the clockwise direction as t increases. Now that we have found r of t, a parameterization, let's go ahead and find r prime of t. Now we have to be extra careful here because our input is negative t, chain rule is lurking. So for example, the derivative of 4 cosine negative t would see two negative signs appear, the negative from the derivative of cosine, and then another negative from the derivative of negative t. Similarly, for the derivative of the y component, we'd have to be careful to make sure that we include the extra negative 1 that appears from chain rule as well. So 4 sine of negative t and minus 4 cosine of negative t. Okay, next let's figure out what the force field would look like with the parameterization plugged in. So no longer negative y, I'm going to replace the negative y with the negative of the y in my parameterization. So negative 4 sine of negative t. No longer positive x in the back. I'm going to replace that x with the x of my parameterization. And so we will get 4 cosine of minus t in the back. Now for a vector field, we're going to need to take the dot product of the force field with this velocity vector to see the degree to which they align. And if I calculate that product, it looks like I'm getting negative 16 sine squared of negative t and negative 16 cosine squared of negative t, which simplifies to negative 16 by the Pythagorean identity. Finally, let's integrate this dot product over the values of t that correspond to doing one loop around the circle. So that looks like negative 16 times t, evaluated from 0 to 2 pi, which looks like negative 32 pi. Now, because work is a physical quantity, we are able to use physical reasoning to check and see whether this answer makes some sense. As a rule, the work done is negative if the force and movement are mostly opposed to each other. So let's scroll back up. Let's have a look at our sketch and let's confirm that a negative work makes sense in this situation. And it looks like, yes, it does. The object is moving clockwise, but it looks like the forces are generally acting on the object in the counterclockwise direction. So the force and the direction of movement are pretty much opposite at every single location, and as a result, we are getting a negative work to reflect the fact that this force is going to overall act to slow this object down and decrease its kinetic energy. Now someone says same setup, but this time I want to reverse the orientation of the object's movement. For a vector field line integral, reversing the orientation has the effect of flipping the sign of the result. And so I don't need to go through this calculation all over again from scratch if I am only changing the orientation of the curve of the direction of movement, it's going to have just the effect of flipping the sign of the final answer from negative in this case to positive. Now, a positive work physically occurs in the situation where the force and movement are overall aligned, pointing in the same direction. And once again, that makes sense in this setup. If I am traveling along this circle in the counterclockwise direction, and if I look at the forces that are acting on this object at each particular location, then I can see that the forces and the object's movement are very well lined up. They are both in the counterclockwise direction. And therefore, it makes sense that we got this rather large positive work done. That concludes today's material. Today we talked about a quintessential application of a scalar field, a line integral of a scalar field, and a quintessential application of the line integral of a vector field. Namely, we talked about how to find the mass of a wire-shaped object, and we talked about how to find the work done by a variable force acting on an object as it moves through a curve.